Hello and welcome to the Ministry of Bridges channel. This channel is about bridges, my bridges, your bridges. Today, I'm delighted to have with me two guests, Andrés and Sebastian. Let's welcome them and have a look into the workflow connecting SOFiSTiK and Grasshopper. My name is Gabriel Neves and this is the Ministry of Bridges. Andrés, Sebastian, thank you for accepting this invitation and welcome to the Ministry of Bridges. Andrés, I'll start with you. Do you mind to make a brief introduction of yourself?
Gabriel, thank you for this invitation. So my name is Andrés von Breymann and I work with SOFiSTiK. I've been with SOFiSTiK for about 5 years, and since January 2021, I'm Managing Director of SOFiSTiK North America. So I moved to the US a couple months ago to take this new task, and I'm very excited. So the topic for today is parametric modeling with Rhino, Grasshopper, and SOFiSTiK, and I want to show you guys this example of a post-tension box girder bridge. These are the components that you can see here on the screen. These are the SOFiSTiK components that I will be showing and using. You can download these components from our website, just following the link that you see on the slide. Once you are in this downloads page, just click on SOFiSTiK Application Manager, and you will get our general tool to download all of our programs, including the SOFiSTiK Rhino interface, which is the one you will need to access these components. So this is what the SOFiSTiK Application Manager looks like. If you go to SOFiSTiK 2020, you can hit on SOFiSTiK Rhinoceros Interface 2020, and you will immediately get the components downloaded. All right, so just a general overview of how Rhino and Grasshopper fit into the entire SOFiSTiK workflow. Some of you might know we have different preprocessors for creating SOFiSTiK analysis models, and these can be AutoCAD, these can be Revit, also Rhino. And in this case, we're using Rhino and we're using Grasshopper, and we're using some other tools like Excel to help us create these models in Grasshopper. The yellow teddy bear that you can see there is our text editor. So SOFiSTiK works with a kind of a text programming interface that allows you to create everything from defining the design code to cross sections to materials to creating the whole model. You may define variables in there and loops and if conditions and so on. Basically, what we do in Grasshopper is we create visually the necessary text input for SOFiSTiK. So we store these text input files, which we can then read into SOFiSTiK and do our analysis, design, and so on. And finally, we can do our post-processing with a typical SOFiSTiK post-processor, system, graphic, result, port, and so on. So let's talk a little bit about the example or the project that I want to show today. So it's a 3 times 50 meter span post-tension box girder bridge, even though the spans are fully parametric, so you can change all of these things. The piers, they have a variable cross-section along the height of the piers. So it's architecturally quite nice. And we have some continuous tendons. They're continuous along the full length of the superstructure. Okay, so this bridge would be a typical kind of span by span bridge sitting on falsework, so to say. So this is the typical tendon layout that you would get in this type of bridge. As you can see on this slide, we have tendons that follow a third order spline. That's the mathematical description of the tendon layout. And we are defining these tendons via a spreadsheet. So it's very easy in Excel to define offset values. In this case, these offsets that you can see on columns B, C, and D would be vertical distances from the bottom of the bridge. And on the column called stations, you can basically define if you want to start creating these tendons at station 0, which would be obviously the beginning of the bridge, station 1.4, which means 40% of span 1. 1.99 is 90% of span 1. 2 would be the support at the beginning of span 2, and so on. So this is how we define our different stations and define the different values for these 3 tendons that we have in each web. So a little bit of how this works internally. This is a picture of our cross-section. We can see some cross-section points defined by their IDs, D0, D1, top center, bottom center, and so on. And we have 3 points for tendons. These points are called T1, T2, and T3, and they are constrained to follow the center line of the web. So that's how the cross-section is defined. It has this variable that is kind of an inclined variable along the center line of the web. This is, for example, how some of those offsets are defined that we saw in the Excel sheet. So in this case, 1.41 meters is the offset, the vertical offset of that tendon T2 from the soffit of our bridge. All right, so next I would like to show you a little bit more in detail how the script is working. And in general, for bridge design with our Grasshopper components, we have this type of work. So the first part is always to create our parametric bridge axis. And this axis will contain information about the road line or the road axis. It will contain some cross-sectional information for the superstructure. It will contain placements. So placements are, in the SOFiSTiK jargon, are points of interest along the axis. So these would be the position of our piers, our abutments, any support conditions, basically planes that cut the superstructure at a certain position. We can even go ahead and define super elevations or skews at these positions and so on. The next component that is needed to define this parametric bridge axis is would be axis variables. So basically any cross-section variable can change not only absolutely, it can also change along the axis. So we can have, for example, the height of our cross-section is changing along the axis for kind of a typical segmental bridge. In this case, that we have more of a span by span bridge, we don't have this variability of the height, but we do have our tendons, which have cross-section points, T1, T2, and T3, which are changing along the axis. So we might as well define those here at this stage. The second part of the workflow is, all right, so we have a bridge axis, it's parametric, it has placements and cross-section and axis and so on. And now we want to extract an analytical model. So how do we define our structural lines, our structural areas, our structural points that we will need it later on for SOFiSTiK? So we use certain components that help us do that. One of those components, for example, is called interpolate line, and it basically will create lines divided at the placements along the axis, and I can use those lines to place my structural lines for SOFiSTiK. So that's what's going on in step number 6 here at the top of my slide. Then we are defining our support conditions. We use a special component called evaluate section, and it basically allows us to slice a piece of the bridge at a certain station and extract a cross-section point at that slice, for example, top center. So I can start grabbing these points at a certain location and define my support conditions, my springs, my couplings, all these things that are needed for the analytical model. So once we have the analytical model all finished up, we can go to the last part. So the last part is just responsible to create those text files that I mentioned in the beginning. So the cross sections will go into the module Aqua. In SOFiSTiK, module Aqua is responsible for generating cross sections. So my bridge superstructure cross section, I need to connect it to the Aqua component, and then I connect that to another component that writes the text file in my project folder, sections.dat. This will be later on included in my main project. The same goes for the structural elements. So my structural lines, my springs, my couplings, all these things go into this component in the center with the M. M, basically it stands for SOFI MSHC or SOFI Mesh, which is our measure. And that's how we create the text file responsible to create this SOFiSTiK model for the mesh. Similar thing is valid for the pre-tensioning tendons. So this is the component with the T on it for tendon. And I will go more into detail live as I show the example file.
Okay, so I can use that this opportunity, and thanks Andres for this introduction. I'll use this opportunity to allow Sebastian to explain to our viewers, just in case you don't know what Rhino, Grasshopper, or algorithm script modeling is. Sebastian will clarify that.
Yeah, thanks, Gabriel. So you saw Andres talking about these scripts and components and stuff, which are from Grasshopper. So let's just quickly explain what that is to those that aren't familiar. So Rhino and Grasshopper, that's a software package by a company called McNeil. Rhino, that's a very accurate and flexible 3D surface modeling software. So you can model basically anything you'd like in it. Now, Grasshopper, on the other hand, that's about parametric modeling and design. And this parametric modeling, that means that you have a set of parameters like, lengths, quantities, coordinates, surfaces, or any other object. And then you have a set of rules that can act on these parameters. And together, the rules and the parameters will generate your output geometry without you having to model anything manually. So then when you change one of these input parameter values, you can automatically get a different design based on that new value without doing any remodeling. So this means that change handling becomes very easy and efficient if you use this parametric design approach. So for example, say you have a bridge that's been modeled parametrically, and then the road alignment changes. Then you can just update your alignment and the whole bridge will automatically adapt to the new alignment. So in the ideal case, at least. So that's what Grasshopper is used for. And as you saw already on Andres' slides, it's a visual scripting environment. And normally Grasshopper will generate parametric geometry inside of Rhino. So this visual scripting, just to shortly go over that as well, in Grasshopper that means that you have your parameters and rules represented by these boxes that we have on screen. And they are also called components. And you can think of these components as functions. So they take some value or maybe geometry as input. They perform a calculation or transformation based on those values. And then they will produce an output result. So you could have a component that takes two numbers as input and it will return their sum as an output. Or maybe a component that takes a road line and a cross section as input and will produce a swept bridge deck as its output. And the results from these components can then be connected to other components downstream to create more complex rule sets. Now, as I mentioned, normally any geometrical output from Grasshopper is being sent into Rhino for visualization. But now with the links that we have from Grasshopper into SOFiSTiK and into Tekla Structures, we can use that geometry output to perform analysis and design in SOFiSTiK or to create actual constructible geometry inside of Tekla. So now I'll let Andres continue with showing what this means in SOFiSTiK.
Great, thanks Sebastian. So you can see here on my screen already, I have Rhino in the background, and I also have a window here showing my Grasshopper script. If I maximize that window, we can see my entire script. Just zoom out a little bit. And here we go. So just like I showed in the slides, we have on the left-hand side, the first part, which is axis, cross-section, placements, and variables. Then we have the central component that defines the parametric axis. On the right-hand side, we have the components that define the analytical model. And here in the bottom, we have the definition of our piers and the analytical model of the piers, for example. On the right-hand side, we have the components that generate text files for SOFiSTiK. So as you can see, I'm focusing entirely on the analytical model for SOFiSTiK in this case. And later on, for example, Sebastian or Gabriel or any Tekla user, they can use some of these same source components and streamline a fully parametric Tekla model as well. So on my screen, I have the SOFiSTiK components already highlighted on the top. As you can see, we have different kind of tabs defining the different steps in the workflow. So on the left-hand side, we have general. So here I can basically define some general global settings for my project, such as the sizes of the the local coordinate systems or the size of the springs and things like that. We have a component, for example, to read data from a spreadsheet or to write our text files. Or this one would allow us to create a basically solve our system, solve our stiffness matrix. This is the main solver in SOFiSTiK called Assay Advanced Solution Engine. In the second tab, we have a lot of information, how to create cross sections. So we are enabling the user to define them in many ways. You can draw them in Rhino. You can import them from a SOFiSTiK database. You can import them from a JSON format. So JSON is kind of a lightweight text input file, so to say, and we are using this to easily create some cross sections, also parametric cross sections that can be used here in Grasshopper. We have some components to modify sections, basically assign variables to these cross sections. Components to simply view the section and check out what are the cross sections points inside this cross section that I can use to define my springs, things like that. Then our next step is structure. So here is where we define our structural areas, structural lines, structural points for SOFiSTiK, and then plug them into the SOFI MSHC component to create a mesh. We have components for loads, and this one to create the SOFI load text input file for SOFiSTiK. And here we get more into the bridge stuff. So we have our axis geometry, where we can define a bridge alignment based on plan view and an elevation. We'll talk about that more in detail a little bit later. And this big chapter is for axis-based modeling. So how do we assign placements to the axis? How do we extract these cross-section slices at any point of the axis to define our springs, for example? How do we interpolate the curves along the axis to create our structural lines? Or even how to interpolate a solid that can work as basically a 3D object that can be sent to Tekla, for example. The final part is the tendon part. So as the name says, how we can create pre-stressing or post-tensioning tendons that work both for Tekla and for SOFiSTiK. All right, so let's get going a little bit more into detail of how this works. Let's move around some sliders and have some fun. Okay, let me create the Rhino window a little bit bigger so that we can see our bridge. And let me zoom into the first part of my script, the road axis. This is the first part of the definition where we define the road axis, and we have created some new components to define a plan view of our axis and our elevation. So for the plan view part, we can define several segments. We can have a straight segment, and then we can have some kind of transition curve, like a clotoid, and then transition into a full arch, and then again a straight part, and so on. So we can build up our bridge in this way. In my case, I'm just having one segment. It's a straight line with 150 meters. The type is a line. As you can see here, I could change this type to something else, like an arch. There's also other options like a clotoid, but in this drop-down menu, I only enabled line and arch. So let's click on arch, and we should see our bridge update relatively quickly. Zoom out a little bit in the preview. We can see the radius is 300 meters. I can change this up to minus 1000, for example. Hit OK. And we can see that our bridge is updating to the new position.
So Andres, here, you can do the same with any 3D polyline in Rhino, right? Or even reading the alignment from the SOFI Plus.
Yes, there are many ways to define an axis. You can figure out how to import the axis from any software, and just as long as you have that axis in Rhino, you can just pick it and put it into Grasshopper and use that for your bridge alignment. As you mentioned correctly, you can also create that parametric axis in SOFI Plus and import it, or now with the new components, you can create the axis kind of natively with our components inside of Grasshopper. The next part would be to define the elevation of my bridge axis. So I already prepared some inputs here. We have a station at the beginning of our axis at the 75 meters and at the 150 meters. And we have different values for the height of these points. So as you can see, they're all in minus 30 meters. But if I change that mid value to minus 35 meters, we have a 5-meter offset at the center of the bridge, and we have a radius of this part of the axis with 2,500 meters, and it's a parabola. So by doing so, we're basically creating a vertical curve. Let's wait for the model to update, and as you can see, now we have a nice vertical curve for a bridge. The next part is the definition of the cross-section. So in this case, I am reading in this cross-section from a text file, with the format .json. And this is being read in from the project folder and read in by this component called read section JSON. The next component allows me to modify that cross-section and assign basically numbers to all of those variables that are inside that text file. So this is a fully parametric box girder bridge, and I can change any of these dimensions. For example, the girder width right now is 9,000 millimeters. I can make that smaller to 8,000 millimeters, or I can make that bigger to 10,000 millimeters. The same is true for the girder depth. So now we have 3,000 as the girder depth. Let's make that some numbers bigger. Okay, so now we have changed the girder depth to 4,000 millimeters. And the interesting thing is that the tendons all updated along the height of the cross-section. And we will see this in the next segment where we define the cross-section variables along the axis, why this is the case. The final component I'm using here, view section, is also very important because it allows us to take a look at the cross-section points that are defined within this cross-section. So let me zoom out and zoom in where my cross-section is being positioned. I can press on this view section component and we can see all these cross-section points being highlighted. So we can see already the tendon points T1, T2, T3, T4, T5, and T6 for the definition of the tendon layout. And we can see also other important points such as top C for the top center of the bridge, bottom C for the bottom center, and some points where the supports are located, which are called S3 and S4.
Let me jump here, and the cross-section is the same. You have more than one different way to add the cross-section into all this workflow. Could be from SOFiSTiK, could be in this case is from a JSON file, and you could do that cross-section, can draft it into in Rhino.
Yeah, correct, exactly. We have different components to do that. I can show you here under chapter 2 section. Read section CDB would be to bring in a cross-section from a SOFiSTiK database. Read section JSON, it's a JSON file. Section from BREP, so you can just create a BREP, a planar BREP basically in Grasshopper, and it can be parametric, and you can use this for a SOFiSTiK section. I will move to the next chapter, chapter 3, which is the definition of the placements. So I just zoomed into the bridge again, and let's go ahead and change some of these placements. So as you can see, we have different stations at 0, at 1.5 meters, at 50, at 100, 148.5, and 150. And these stations have names, and the names are start, centerline abutment 1, centerline pier 2, pier 3, abutment 4, and end. And finally, they have types. And the types basically allows us to tell the program where we have supports. Okay, so we have supports at 1.5, at 50, at 100, and at 148.5. And by doing so, I can tell the program that we now have span stations. And this is how I'm defining my tendons later on by span stations. If you remember from my presentation, we had a tendon low point at span station 0.4, which would be, or 1.4, I think, which would be 40% of span 1. Let's change some of these values. For example, let's move from 50 to 20 and make a much shorter span at the beginning of the bridge. As you can see, our bridge updated, and even our tendons have updated because of those span stations. The tendons are defined by the span stations, so now we have a very different tendon layout. If I go to a top view, we can even see that the tendons are moving not only vertically, but they're moving also transversely because of the inclination of the tendons, of course. If the tendons are at the top of the web, they're also a little bit wider. So this can be seen very clearly here on the top view. Let's change again, maybe to 30 meters. And we can see how not only the pier is moving, but also the tendons are getting wider at a different location. Fully parametric. And this location, you would also be able to create some rotations of these planes to create skews and super elevations. But in this example, I don't have any of that. Let's move to the last part of this first chapter, 4.1, definition of axis variables. And these are my tendons. So here is where we are providing that Excel sheet and we are defining different values for different stations. Let me go to my project folder here in File, Show in Folder, and I will open the Excel sheet where I defined my tendons. And now I can show you live what happens when I change some of these values. Let's go back to a 3D view. And for example, let's change this first value of one of these tendons, station 0, instead of 0.58, let's say 0.7. Press OK. So far nothing changes. I just need to hit save in Excel, and I should see the change happening live in my Rhino preview. There it is. Next, let's change maybe some of these station values. Instead of at 40% of span 1, let's say 70% of span 1. I want to have my low point. Let's hit save and wait for the change to happen. There it is. So as you can see, we have a very powerful tool to create all kinds of tendon geometries. I can close the Excel sheet now. These values that I defined for my tendons, they are depending on the height. So I'm actually multiplying those values by the height of my bridge, which is 4,000 millimeters, to finally provide this component with the accurate values. So if I change the height of my bridge, my tendons will also be changing. I have another input possibility here under types. So I can choose to have a spline distribution, or I can, for example, change that to a linear distribution. And our tendons will now be straight instead of parabolic. Okay, let's move to the next part of the script. This is the component that collects all the information that I just defined and creates my parametric bridge axis. So this is the most important component in the workflow. If I click on it, I get a preview of the stations and the station names and some further information. For example, is that station the beginning of the bridge? Is it a support? If it has the letter S after type, it means this is a support. And now I will use some of these axis-based modeling components to start creating my analytical model. So let me just show you a quick example of how that works. I can choose any of these components: evaluate section, interpolate curve, interpolate solid, or interpolate surface, to create my analytical model or my 3D geometric model, which can be sent to Tekla. So for my analytical model, for example, I choose evaluate section. I insert that component. I connect the axis to it. And now it's evaluating or retrieving a slice of the bridge at the beginning, at station 0. So let's change that station with a slider that goes from 0 to 50 to 150, which is the length of my axis. I hit OK, and I can connect this slider to my component. As you can see now, this point O has been retrieved at station 50. I can move this thing around, and I'm being able to extract that point at any location along the bridge axis. If instead of the point O, I want the bottom center, for example, I need to provide a text panel with the text bottom center, and I connect this to the component. And now we have the point bottom center. In the next part of the script, we're using the component interpolate curve to create individual curves between the placements at exactly the cross-section point top C, top center. So if I click on that, we can see this green line highlighted exactly at the position top C along the bridge axis. And if we provide a text panel and take a look at what's being created, we can see multiple tree branches, each for each line between the placements. The next component is the typical SOFiSTiK structural line component, which I can use to provide a group number, a section ID, some fixations, some element types. Is it a beam? Is it a cable? Is it a truss? I can click on it, and we can see highlighted the things that I provided as information. So the group ID and the section ID are being highlighted, but also the local coordinate system of these structural lines are being highlighted. So this is the superstructure. Now let's go ahead and look at the substructure or at the springs. Here we can see the support conditions for the piers. First of all, we're using the evaluate section component, and we're evaluating, for example, here at top center. And we can see the station is not just a number. So I am also able to provide a string. And this string is basically the name of the stations. And if you remember, we have some stations that are named Pier 2 and Pier 3, I think. By providing Pier star, I'm telling the program, please evaluate at all stations that begin with the word pier or that have the word pier in the section names. So we're evaluating those two, basically those two piers. If I were to change that to something else, for example, a butt star, then I would expect those components to evaluate the location of the abutments. Press OK, and we can see, well, these things moved. We don't really see it because I also have a similar definition at the abutments. Anyway, here are our piers being evaluated at top center and at the points S3 and S4, which represent our substructure locations. And I can use these two components, the top center and these two bottom points, and I can use a coupling component to connect them with a rigid coupling. As we can see, the top point, the two bottom points, and in between we have our rigid couplings, which are in group 20 and have the fixation type F. So in SOFiSTiK, the F stands for please fix all degrees of freedom. In a similar way, we evaluate the two bottom points, and we can simply copy these points vertically by 25 centimeters and create an elastic coupling that basically represents our elastomeric bearings. And I can provide some properties such as, again, the group number, the axial stiffness, the transversal stiffness, and the direction. The next thing I want to do is I want to be able to connect my piers, my analytical piers, to that exact location. So first of all, I want to find a line in between those 2 points. So I use a polyline component, and then I find the curved middle point. So I find exactly that position where I want to connect my pier. And now I create another coupling from those bottom part of the bearing pads to the top of my pier. Let's have a look at the abutments. The abutments are actually very similar. So we have the same philosophy. Top point, two bottom points of the supports. We have the coupling. Then we move by 0.25 elastomeric height. We create our elastic coupling. And the only difference is now we don't have gears connected to the bottom of that location. We just have our abutments, and we just want to represent them with 3 springs, 1 for each direction. So this first one is our vertical spring. This second one would be our longitudinal spring. And this third one will be our transversal spring. And the nice thing about Grasshopper is, I can take data from any location. In this case, I want to take the orientation of the plane to orient those springs as well. Okay, I don't want these springs to be oriented globally. I want them to be oriented locally with the bridge axis. So let's go to a top view to make sure that it's working as expected. So I'm zooming in at the end, and we can see they are actually aligned with the bridge axis. And how do I do that? The evaluate section component can also provide the plane information. And this plane information, I can connect it directly to the X direction, or I can multiply that with a vector product or a cross product to get the transversal direction. Of course, I need to multiply the vector, the vertical vector. So the A input would be the plane direction, which is along the axis. The B input is the vertical vector, and I get by default the other direction of my right-hand rule to get this transversal direction. So the final part of this script that I want to explain with regards to the analytical model is the piers. So the first thing I'm doing is I'm reading a cross-section from a JSON file, and this cross-section is creating a rectangular section or kind of an oval section. And the neat thing is in this workflow, I can define my pier at any location, and then simply I can transpose or transform that peer to the final locations of the peers, but I do that later on. So as a first step, I just create my peer anywhere in space. So I'm reading that one cross-section from a JSON format, and I'm using the modify section component to assign some variables to this cross-section. So I assign peer top section height, for example, and a peer top section width. So this is my first cross-section. We can visualize it here with the view section, and we can even change some of these values. Let's say, for example, let's make it a lot bigger or a lot smaller, or even the width of it, we can change it up. It doesn't matter what change I make. We'll just reset these changes. So from one single JSON file, we're creating 3 cross-sections with different values, 1, 2, and 3. And we can visualize them here. 1, it's being copied downwards by 2 meters to this location. Then I have another definition, which is located 5.6 meters lower than the first one, and this final location, which is at 13.6 meters downward. So finally, what I do is I extract the center points of all those 4 cross sections, 1, 2, 3, 4, and with the polyline, I can define a line that goes exactly through those points. And I can already connect the SOFiSTiK structural line to that. And I can even assign the cross sections 11, 12, and 13. And if in SOFiSTiK we provide this type of input, 11.12, that means the start of this beam should have cross section 11. The end of the beam should have cross section 12. So we can see it already here. This is a cross section that is constant at the beginning, then it gets a little thinner, and then it gets a little thicker again towards the end. We also provide the support condition for this peer here at the bottom of that location. Okay, so this has been created anywhere in space. How do we transform that to the bridge location? And basically, we're using this component called placement transform, which I can basically create the mathematical transformation needed to move any geometry to this new location. So I'm using the Grasshopper native component transform as well, but I just need to provide this mathematical transformation, and this is provided by the SOFiSTiK component. So we have the axis as input. We have the point where we want to connect that to, which is bottom C, bottom center. We have the stations here, which we want to connect that to. And we have a source plane, which would be that plane where I created my original geometry being connected here. So all that information is being streamed to this transform component, and this ultimately will move any definition that I created in space to that specific location. So let's test it out and change the name here from peer to, for example, abut. Press OK. And as you can see, the peers are now located at the abutments. Or I can provide here 70 for 70 meters. And you can see the peer is now located at that location. The next part of the script that I want to quickly talk about is the pre-stressing. So the geometry for the tendons has already defined in the cross-section part with the cross-section variable. So we basically just need to call these tendon IDs into our component tendon geometry, and we already get the right location for these 6 tendons. And we have other components which we're using to add some properties to these tendons. I think I'm not going to go into detail in this part right now. And finally, you can connect that to the SOFiSTiK tendon component and create all the necessary information to run this later on in SOFiSTiK. Here, a little bit higher in my script is where I create these text input files for Aqua, which is our cross sections, design code, and materials. And here is the data generation for SOFiSTiK for all my structural elements, all my geometry. So let's go to the SOFiSTiK project, actually. This is my SOFiSTiK working window. This is called the SOFiSTiK structural desktop. And here I'm now in the SOFiSTiK world. I'm not in the Grasshopper world. I can define here materials and cross sections as well, or I can start importing things from Grasshopper. This is what I'm doing here under text input for modeling. This is a task in my task tree in SOFiSTiK. and I can start including some text files that are stored in the project folder from Grasshopper. So hashtag include sections, hashtag include geometry, and include tendons. So if I run this task, I can right click on it and I can calculate it. Then we're running all those text files directly from Grasshopper, and we should get a new updated SOFiSTiK model. Calculation is finished. So we can click on system visualization, check out our new updated model. We can change the visualization to not see the cross sections, and we can easily see the tendons. Or we can even show this type of visualization that allows us to see exactly where those tendons are crossing our beams, and we can see they're perfectly at the middle of the webs as intended in the Grasshopper script. Okay, so I have calculated everything. I calculated some load cases and I ran a linear analysis, and then finally I ran a construction stage analysis, typical SOFiSTiK tools. So let's have a look at some of these results. Zoom out a little bit. So we can click through the load cases, show dead weight deformation, additional dead weight, some variable loads that I have defined, and we can see also our curvature loadings. So for the construction stage analysis, we have in SOFiSTiK individual load cases for every single stage, and we have accumulated load cases. So the individual load cases are stored in 5000 series, and the accumulated load cases are stored in the 4000 series. Why do we have these two groups? Basically because if we want to check how the bridge is deforming in real time, for example, we want to see the total accumulated deformation. So we check the 4000. But what happens if we want to check the bending moment only for self-weight, or only for pre-stressing, or only for a certain creep and shrinkage stage? We need this to run our combinations and do our design checks. So that's why the program also provides these individual results and stores them in this 5000 series. So let's go ahead and click through the accumulated results first. The first load case I have here is 4010. We can see a huge deformation of the piers. Of course, this is a little exaggerated. So let's fix this amplitude to 100 times the real deformation, for example. Then we can stop the animation. Okay, so this is this first load case. The next load case, 4015, is creep and shrinkage. So we can see we have a little bit of a shrinkage of the piers due to their own self-weight, basically. Next, we add the whole bridge. It appears in one go, for example, and its dead weight is activated. In the next stage, we add to this existing deformation, we add the pre-stressing loads. So we can see our bridge is deforming now a little bit upwards. So this is the previous load case. After pre-stressing, it deforms upwards a little bit. Then we have some more creep and shrinkage. So the bridge, again, will creep and deform a little bit more. We can add in the next stage some additional dead load, and finally add some more creep and shrinkage stage until the bridge opening, for example. And this would be the final stage. And in a similar manner, we get the individual load cases. So this is only the piers, only creep and shrinkage of the piers. Here we see only the self-weight of the bridge deck and its deformation. Here we see only the effect of pre-stressing and so on. So at this stage, I'm done with the SOFiSTiK part of the presentation, so I'm open to any questions, Gabriel, you might have, or Sebastian, please go ahead.
Yes, Andres, thanks. I really loved your presentation and demo and tutorial, I guess. So I have one question that is to do with the components in Grasshopper or Rhino and SOFiSTiK. So when I tested my SOFiSTiK license wasn't working, so I couldn't load those components. So what's going on?
Probably your SOFiSTiK license expired, so you just need to renew that one. So I think that's the issue. Basically, you don't need a full SOFiSTiK license to run the SOFiSTiK components. You only need the license for the Rhino interface license. So if anybody is not a SOFiSTiK user but does want to use the SOFiSTiK components to create parametric bridges in Grasshopper, they can download the Rhino interface module, and they can get the SOFiSTiK Rhino interface license. And with these two things, they can work. So they don't need to install the full suite of SOFiSTiK tools if they're not doing the finite element analysis.
So that means it opens the door for the companies that they have the workflow with some designers doing the analysis and all that work with SOFiSTiK, and maybe one Grasshopper developer that is just building the script. So they can have then, they don't need to have the SOFiSTiK full license installed in the machine of the Grasshopper developer then.
No, and he doesn't need the full SOFiSTiK software itself either. So only the license of the Rhino interface and only the software.
I think that is great news for our viewers. The second question is to do with, so I'm in touch with you with this and having these components connecting Grasshopper and SOFiSTiK for over a year already, and I've seen how much this evolved. So the question is, are we there yet, or do you still have other ideas to keep developing these components further?
No, this is a work in progress. There's still a lot to do, and it's a very exciting project, and we're excited to keep going. So we're not stopping anytime soon.
Yeah, I was just thinking along the same lines. So we see how you bring over all these nice structural elements and tendons and stuff. But what should I do now if I notice that my favorite feature of SOFiSTiK isn't supported in Grasshopper yet? Like, should I just come shouting at you guys, or are there any ways to speed up that?
Yeah, that's a good question, and this kind of shows the power of Grasshopper as well as more of a kind of programming language. So in the end, what we're doing is we're creating a bunch of text input files for SOFiSTiK, and these text input files, they can be created by any user. If they have a little bit of Python knowledge, for example, and there's a missing feature in SOFiSTiK that they want to run from within Grasshopper, they can do it themselves. Of course, we're happy to get the feedback, and if it's something that we see value for many people, we will take that hint and do it ourselves maybe, but you don't have to wait for us. You can do it on your own too. Here in the Grasshopper, if you go to SOFiSTiK and you hit help, then it will take you to our website, and it will take you to the help or to that documentation of the Rhino interface. So it has a little bit of information, what is Grasshopper in general. It has some workflow tutorials. For example, the one I'm showing you today is this one, post-tension concrete box girder bridge. It has a nice step-by-step written tutorial that you can follow and create your own. One more thing I want to show you is here we have a nice command reference also. So if you don't understand a certain component, just go here to the command reference. You can find it. For example, I don't know, let's look at the axis variable by points. We click there, and there's a full description of the input and the output of the different components. You can also access this website from the components themselves. So, for example, here, structural line, I can right click, hit help. There's a little bit of a description of the component, and if you scroll down, further information, it will take you exactly to that command reference for this component.
Oh, that's neat actually. Yeah, I mean, this looks really good, Andrés. I can't wait to start trying to match now what you have there with the Tekla components to try and get that constructible BIM model going. I guess we'll tackle that in the next episode. Is that right, Gabriel?
Yes, the following episode will be about now closing this part of the workflow. Grasshopper to Tekla Structures, truly constructible model. What an amazing tutorial interview demo that Andrés just offered to us. Thank you very much, Andrés and Sebastian. Next episode, we're going to have Sebastian, and he's going to show how to take now this information and keep developing the script in preparation to send it to Tekla Structure software. Leave as many questions as you want for Andrés, and if we have more than 10 questions, I'll bring Andrés along again, and we have a QA session just with your questions, the Ministry of Bridges viewers' question. See you on the next episode, and have a Bremer day.